Okay, well, hello everyone. I'm Gail Safey and I'm the president of the Durand-Hedden House and Garden Association. And we are so pleased that everyone is here today to learn about a multiple syllable word called dendrochronology. This event is actually, and the whole exploration was made possible by a grant that we received from the New Jersey Historical Commission and the Essex County Division of Cultural and Historic Affairs, and we're so grateful for that grant that it made today possible. I also want to mention that we are starting to do a fundraiser for the roof of the Durand-Hedden house, because one of the reasons we wanted this dendrochronology exploration was to inform what we do as we have to replace the roof. Susan, please. No, I have a few sorry. Now, Michael Cuba is an associate of the Oxford Dendrochronology Laboratory in Oxfordshire in the UK. He is now living in southeast Pennsylvania, but he began working as a preservation timber framer in northern New England in the early 2000s. He spent many years studying traditional joinery and vernacular architecture before co-founding Nob Hill Joinery in Marshfield, Vermont. And then he began to shift his work toward assessments, non-destructive evaluation, and documentation of historic properties. So we are so lucky to have him. In 2013, he started working with Dan Miles of the Oxford Dendrochronology Lab, and this culminated in the establishment of Transom HPC, a historic preservation consulting company. Michael is also a co-editor of the Timber Framing Technical Journal, and he has a leadership role in the Timber Framing Guild. And he serves on several boards and advisory boards, including the National Barn Alliance, the Historic Barn and Farm Foundation of Pennsylvania, and several local historical societies and municipal historic advisory review boards. So thank you so much, Michael.
Thank you all for coming. Thanks for the introduction. I think you covered most of what's up here. I don't think I have to talk about that, except let's talk about dendrochronology. Break the words down. Dendro is of or relating to the study of trees, and chronology, it's time. So it's kind of tree time. I will tell you that dendrochronology started just over 100 years ago in Arizona by a guy named A.E. Douglas, who was an astronomer, and he was studying climate. And he was curious to see if within the wood, if he would be able to detect solar flares, sunspots, patterns of solar activity. And that was the reason that he had initially developed the science of dendrochronology. Arizona is still a world hub for dendrochronology, and most people who are doing this work are climate scientists. They're looking at wood to tell us about the history of climate over time. The architectural dendrochronology is sort of a side thing. At the moment, east of the Mississippi, I think there's myself, a fellow named Mick down in Baltimore, and a guy named Bill Flint from historic Deerfield in Massachusetts, and I think we're the only ones who are doing architectural dendrochronology at the moment. There have been some others. So generally what we do is we're looking at wood, and we're looking for patterns in growth rings. So here you can see you've got the bark, you've got an annual ring here, and what we do is look at the rings, and you're looking at skinny rings and fat rings and looking for patterns of essentially wet and dry, and looking at those patterns in samples and attempting to match them up with other known chronologies. So this is what I look at when I'm not out taking samples, when I'm sitting at home looking under the microscope. I'm often looking at oak, and oak is a ring porous wood, and you can see these big pores there. And so this is the early wood, and then there's late wood here. So from here to here is 1 year's growth, and you're starting here and it's growing that way. And so these are the rings that I would look at and measure to see if I can get a pattern or a climate signal. We do also look at softwoods, and you'll see this A and B here. So on the right, you've got sort of a semi-diffuse porous hardwood, and you've got A is the early wood, the spring wood growth, and then B is the late wood. Then over there, you can see this is probably pine, and you can see that the early wood is much more of the ring, and the late wood is much less of it. And the reason for that is that the evergreens have needles all year round, so they've kind of got a head start. They do have some reaction to the seasons, but not in the same way that an oak or another tree that drops its leaves would have. By the way, I'll take questions anytime. I'm trying to have it be conversational. If anybody has questions, I'm happy to answer as we go.
So what are those distances there? What's the thickness there? 80?
So yeah, what the A and the B are showing are A is early wood, and you can see that it's significantly larger here and smaller over here. So it's smaller where it's the hardwood, and the reason is because there's no leaves on the trees when it starts those early pores, and that's why you get such a big jump with some of the softwoods. And then B is the late wood.
What do you mean by early and late? Like, what does that mean?
So during the growing season, in the spring, you'll put on this wood that has the large pores.
So early in the season is what
Early in the
refers to?
season, yeah. So right now, the trees are putting on their early wood growth. So the pines are doing this. They're growing really fast. The hardwoods are growing quite a bit slower, and it's not until you get into May or June that they start putting on growth like this. I will say that we like oak in particular because it starts putting on these big pores early in the season, regardless of whether or not it started to leaf out. So for some tree species in a drought year, you may not have an obvious ring, but with oak, you'll always have the early wood, but you might not have so much late wood. And so sometimes when I'm looking at samples, I see big pores like this right up against another group of big pores like this, and I'm straining to see this line that distinguishes one year from the next.
Is that growth underneath the bark? Like
Yep.
where it's under the bark?
So I'll go back here, and so you've got the bark here, and then you've got, I can't tell from these striations, but it looks like this would be late wood here, from here to here, and then a band of early wood. So I'm assuming this is one ring in this illustration, this is the next ring.
And that line, when you say this, the beginning of the year, is it typically March? Or is it?
Depending on where in the country
Okay.
you are, pretty much when the snow goes away. When you see the daffodils come out, that's the beginning of the year for these.
Okay.
How does the bark accommodate the growth without cracking or like?
Oh, it does. It does. It cracks.
And then does
it
it create
moves.
new bark? Does
Yes.
it fill in like
Yep.
with new bark? Okay.
It keeps getting bigger. There's a lot of different kinds of bark, different varieties. We generally don't get to see a lot of bark, and sometimes when we do, when timbers still have their bark on it, bark is really good for holding in moisture in the sapwood, and it's a great place for insects to congregate, and so sometimes they'll do damage to the wood immediately below the surface of the bark. Okay, there's another example. This is diffuse porous hardwood. Not all wood cells look the same underneath of the microscope, and so you can see here you've got heavy pores right on that early ring line, and then here it really is diffuse, where those pores are spread or distributed somewhat evenly. So I'm looking for these discrete little lines to indicate the beginning and the end of, we say a year, but we really mean a growing season.
And the
So-
pores are when it's growing, like really growing
Yep.
actively.
Yep. Yeah, in the wintertime, they are here, they're generally asleep. There's not any growth. When the leaves fall off, that growth really stops. They go dormant for the winter. So what I'm trying to do when I'm assessing a house and looking for samples and taking a sample out of a timber is get as many rings as possible. And in order to do that, I'm trying to get from the outermost ring and the outermost surface of the outermost ring, because that is what was present when the tree was cut down. And that's how when we're dating houses, that's what we're looking for, is the felling date. What was the season of the year that the tree was cut down? And then we know that the house couldn't have been built before the tree was cut down, if that was part of it. So that's what we're looking for. So this outermost ring is the most important. Second most important thing is number of rings. If you think of matching up patterns of wet and dry, if you had a short sequence like 3 or 4 rings, and you say wet, wet, dry, dry, you can match that a lot of places in a long sequence. The longer the sequence in your sample, the more complicated it is and the harder it is to match up, which means you'll get a better signal or a stronger result. So to do that, we want to get from the outermost ring to the heart if we can. It's okay if you don't actually get the heart. And the reason I threw this slide in was to show that the heart is not always necessarily in the center of the tree. And so wood reacts, trees react to their environment. If there's a persistent wind that it's facing, or it's on a hillside slope, softwoods and hardwoods react differently. Hardwoods will put on wood in tension to resist a force, whereas softwoods will put on wood in compression to resist the same force. And so as a result, when you see somebody makes a square timber out of this, it might be that the heart that you would think is going to be in the center is off center a little bit. And so that's part of my job, is to find where is the center. I can see there's a piece of wood right here in the wall, and you see there's a check along that piece. Checks are cracks that happen. You can see there's some checking here. If you think it's wet in the center, and it's drying from the outside. So this is not shrinking, and then this is. That's how the checks start forming. And the checks always take the shortest route to the heart. So when I'm trying to assess timbers in a structure, I'm always looking to see where are the checks on the surfaces that I can see, and I can use that to triangulate roughly and make my best guess if the heart happens to be off center. So any questions before I get into regional chronologies? It gets simpler as I go. I'm trying to get the science out of the way in the beginning as much as possible. So in order to make matches, we can't take somebody's word and say, oh, we know that the Durand-Hedden house was built in 1787 and whatnot, so if we take a timber from there and we match it up, that must be the date. All regional chronologies start their development from a living sample. So you got to be able to verify this tree is alive in 2025, and you can literally count the rings backwards. You're going to measure them, record them, but you're counting backward from a known living point of reference. And then you can start overlapping if you get good matches and good overlap sequences. So for a living sample, say if you can get a tree that's 350, 400 years old, and then you can match that with another sample of wood from something that you suspect might align with it, and you get an 80 or 100 ring overlap, and it overlaps really strongly, then you might be able to start working backward into time. So on the bottom here it says 1900, and you're working back to the year 1800. In some cases, in some locations, we've got chronologies that go back many thousands of years. Yep?
Have you had any information or data on chronology in other countries?
Yes. One thing that dendrochronologists are really good at is sharing, which is useful. There is an international tree ring database, and so you can look on any continent on the planet, any place where trees are grown that put on annual rings and information has been recorded, there is likely to be some information in the tree ring database. Locally here, I expect that like a house like this, theoretically is going to be built with materials that were locally sourced, probably right on the property. As you get into the 19th century, you get things that have been sent from upriver, and so we might be looking at chronologies that are 100 or 200 miles away or in a different region. Generally here, I'm not looking at chronologies in other countries. I did data a panel painting in New York recently, that was believed to have been an original painting of Queen Elizabeth I, that she had sat for it, and we did date that, and it was French white oak, and we weren't able to date it. And it took us a while to figure out. We were looking at English oak and then Baltic, and it was not there, but we did find a match in France. So, and the material is very
Is that not
important.
completely automatable though?
Which part?
Well, once you have the sequence from your sample, can't you just compare it to absolutely everything in the database and look for the matches?
Yes.
So it's a Perl script.
Yes. You can definitely,
Right.
you can run it against everything. We tend not to. We do tend to compartmentalize a little bit. So for here, like doing the Durand-Hedden house, I looked at samples from Georgia to Maine, and it's about as far west as either Illinois or Indiana. Not so much further than that. We're not expecting that the material is going to
But
be.
depending on how the database is structured, you would just sweep out a box and say, yeah, I've got something that I think might be from something in this box.
Yep.
Run it against all 10,000 samples that happen to fall in that box.
Yes, we
And
can
for,
do
the,
that.
and for the painting, you would just choose the box to be Europe, and for here, you would choose the East Coast.
Yeah. And I will say, for simplifying, if you're using a lot of chronologies that you know aren't going to be relevant, it does put a little bit of static and chatter in the results. It also slows it down a little bit. Like at this point, computer speed is enough that I can get away with it on my machine. The guy I work with in England, he's using a slower machine, and it would take a couple more minutes to go crunching through the whole world's worth of chronologies. But the point here is that the chronologies have to start from a living sample and work backwards. And it's not one sample. We would take several hundred samples, and then you match each sample together, add all common rings together, and divide by the number of common rings to get an average. So when you're looking at a regional chronology, it's not a regional chronology that's actually developed off of one tree, one windmill, one tithe barn, what have you. There are usually several hundred or thousands of samples that are actually going into these chronologies to be averaged. Some are kept as sets of independent chronologies. There are some folks in New England who are, they're studying climate mostly, and they have a habit of every time they get a match, they add that into their chronology, and then you can see there are histograms that show all of the common rings, and so you can see which ones have been averaged and how many individual samples of rings went into creating that average.
When you talk about taking samples from a live tree, are you doing like a core sample?
Yeah.
And how big is it so that it doesn't damage the tree?
It's about 1/4 inch. I
so
did
it's
it
pretty small.
when I was at UVM, and I had no idea why I was doing it at the time, which means I probably just wasn't paying attention in that class. But they sent us out in the woods with these neat little tool called increment borer, and so I put the increment borer together, and it's sort of like a T, and you twist this thing, and it goes into the tree, and same strategy. You're trying to find the heart, you're trying to get the most rings possible, and then they were brought back to the university and measured and recorded, and presumably those are in some of the data sets that I use currently today. Yeah.
Are there any trees in the United States that you cannot touch because of that? Because
Oh, I'm sure.
there are, various species in Australia and New Zealand. You don't go pushing a hole in there, otherwise you go to jail.
I'm sure there are. I will say, for my part, I am not involved with creating any of the regional chronologies, and at this point, the data sets that we have they're pretty robust. So I've not been in a situation where we thought we should go develop a regional chronology. I work mostly from Virginia to Maine, and we've got a lot of data. This is always fun because there's always somebody in the room that's really into math. So if you want to know how exactly we're doing this, so I'll tell you, there's what's called Student's T-Test. Student is a pseudonym for a mathematician by the name of William Seeley Gossett, who was an employee of Guinness And there was a question when he developed this, this statistical means of testing as to whether or not sharing this would be divulging a trade secret, so he published it under the name Student. Guinness agreed that they weren't really giving anything up and that their beer would still be superior and delicious if he gave this equation away. But the student's t-test can be applied in a number of different ways. But it basically asks the question of, is this similar to that? Is this group similar to that object? Or are these two groups similar? And what we look at in particular, I will say for dendrochronology, we do use students' t-tests. We also use a modified version, which is called Bailey-Pilcher t-test. There's two Irish statisticians developed in the 1980s. And what we're looking for, and this will be important as we go on, I'll try to keep the math to a little bit of a minimum, but when you see this threshold, 3.5 of a t-value, that indicates that there's a correlation or a match between a sample and another chronology that is statistically significant. Theoretically, if this has 80 rings, then you have a 1 in 1,000 chance of having a spurious result. And I will say, I see this 1 in 1,000 chance of a spurious result 100 times a day. So it does happen. So 3.5 really is the baseline for where you start paying attention in these results. But mostly, we're looking for a lot of replication. We don't want to match one sample against one chronology and say, we've dated a building. You want numerous samples against numerous chronologies. But essentially, like I was talking about earlier, about, say, wet and dry, that's sort of what you're looking at and matching up wet years and dry years between your sample sets and regional chronologies. But you can see here where it's misaligned. You notice where it is well aligned, it's not perfectly aligned. And you're never going to have it really perfectly aligned because the same tree will grow differently on this side of the street than down the street, whether it's different soil types, different availability of moisture, different wind access, how many trees are around it, how are they growing, and then changes in the local environment that are going to affect growth. So you're sort of looking at larger patterns of wet and dry. And I will say that these graphs get largely regularized. The static gets filtered out. So these are filtered graphs that I'm showing here. I threw in this not just for fun, but just to show you how we're formatting. So what we have at the top, I think this is an undated sample. The date would go there, but it's saying you've got 60 rings, and you see we've got 6 rows of 10. So as we're measuring, and I'll show you how we do that, we are recording, and every 10th ring we jump to a new line. And so this sort of helps us keep track of where we are. We mark off each individual core first manually. So, and in the case of my program, I hear like a knocking sound when I get to 10. So I need to look up and see if I get to 10, there needs to be a little mark on that ring. If there's not, then I got to look for a mistake, and hopefully that limits me to finding that mistake within 5 or 10 and making a correction. And then on the bottom, you see there it says 1/4 C. And so we make those kind of indications that show what part of the year. So this 1/4 C tells me that the sapwood is complete, but it's not a complete year's growth. The 1/4 indicates that it's just those early spring vessels that have gone on. And then of course, what species, although I will say we generally for oak, it's not necessarily red oak, but red group and white group is what we're looking at. It doesn't make that much difference in terms of cross-matching. See, I told you it was going to get more fun. So the things to look at here. So on the left-hand side, you've got, these are abbreviations for various chronologies. These are the date ranges, which don't necessarily indicate the age of a building that's determined or interpreted. the end of that date range, 1712, that could be something that's utilizing a repair timber. We may sample things that we know are probably past the date of the structure, just to broaden our range and better the chances that we're going to have for matches. So this gives you a range. The next column over here is looking at overlap, which is particularly important to see. That's okay. How many rings of, I'm just glad it wasn't me. How many rings of overlap do you have? So if you have a sample that's got 93 rings, are all 93 overlapping where you've got this match? Or is it something really low, like you see 47 there? And then what are the t-values? And here are those t-values. Remember, 3.5 was that statistically significant threshold. And then here are the dates. And so here you can see where you've got 4.94 to 5.05. Those are considered statistically significant, but you've got matches here at the year 744, 877, 1650, 1673. So you don't have a lot of good replication there. And these are all spurious matches. And this is why we want to go against multiple chronologies, that you don't want to just look at a single one. And you want to use multiple samples. You want multiple matches at really high values. And even at these values, 5.47, 4.5, that's pretty good. It's not great, but what makes this a reasonable match, you see all of them are concluding 1713. So they've got, that date is in common. So that seems like it's a pretty reasonable match. And then you would look at where's the house that you're dating, where's the Bradford house, and are these in its region, or are they a bit far flung? Does it make sense? So you look at the geographic distribution of the matches.
What was the significance of the date range on the left side? I don't understand those.
So,
because some of them end before 1713.
Yep, yeah. So you can do that. So you can have, say, a chronology that goes up to 1680, but you've still got a good overlap with it. And so
Up
you
to that
match
point.
those rings so you can conclusively date 1680 is identical, and then you could literally just add the rest of the rings on and say, okay, well, you've got X number of rings beyond the range of that chronology, and that gets you to that date.
I see. But what's the range? Like, what's the beginning date and the end date? What's the significance of those?
So, like here, 1527 would be the earliest ring recorded in that particular master chronology.
Okay.
And then 1712 will be the last date recorded in the master chronology. And each of these master chronologies tends to be built up of multiple chronologies. So if you opened up CHN 13, it could be comprised of 50 individual samples. And so this is, you take all of the overlapping samples and divide them by the number that they have in common to get those measurements, and it helps sort of filter out the noise, and that's how you make the masters. Not every sample goes into a master. You might find that we took 10 samples, 8 of them match really well with each other, and 2 seem like outliers. And you can try building the master and running that, so you build a site master, which we did for this house. We'll talk about that in a bit. And so you take the site master and run that against the regional chronologies, and you can add in individual samples and say, does that strengthen the signal or does that weaken the signal? So you may say, we've got 8 out of 10 dated conclusively. We've got 2 others dated conclusively, but not part of the site master, or they didn't date at all. That's it. I don't think there's any more math. I think
Now we get to the fun part.
yeah. So, how do we do the sampling? So we use a hollow coring bit. There's no lead screw or anything, so we use a little template to center it. You don't want to abrade that outer surface. This outer surface is the most important part. That's the thing that's going to give you that felling date that you need to make a determination as to when the timber was cut down. And so what we do is we drill very carefully, very slowly until we're through the sapwood. And then once you're through maybe the first inch or so of wood, it starts to stiffen up when you get into the heartwood, and then we'll throw on a hammer drill. And so we are engaging and then withdrawing carefully to expel dust. It's not like a fluted drill bit that can pull dust out on its own, so we need to be really careful to make sure we're extracting. If we can, we try not to drill down, prefer to drill up so that gravity can help expel the dust for us.
How do you know that the outside of that beam is the date that the tree was felled? I mean, it may not be the outside ring.
Right. So here I can see that it's not super uniform. It's there's some undulation in it. I can recognize the outside layer pretty well by eye. But every once in a while you'll see something where somebody debarked a log with a draw knife before they hewed it, and that what you think is a waney surface is actually been knifed off, and so you might not have that outermost ring. When you're looking under the microscope at those rings, if you see a straight line across the end, definitely not the outermost ring. There's going to be some movement, specifically that there are these medullary rays, these rays that go from the outer surface toward the center of the tree, and each place where you see a ray, there tends to be almost like a meniscus type of effect with the growth there. So you should see that sort of irregularity in the surface of the ring should carry to that outside surface. But the short answer is you get an eye for it. I carry around a jeweler's loupe. If I'm not sure, I try to look a little closer before I start coring. But raking light will often do it, and you can see even in this light, I can see the shadows cast here, and that tells me this is not a tooled surface. And that's really what you want to see, is that once you get started, that this doesn't disintegrate. And that happens to us a lot if there's a lot of powder post beetle damage or rot, that this outermost couple of rings is pretty prone to decay and damage, and sometimes it just disappears on you. So one of the things that we're always looking at is how a timber is cut, and depending on the relationship of the cutting of the timber to the piece. So in all of these, here you've got boxed heart, which is pretty common, especially in the United States and in New England, where you cut a tree down and the heart is roughly in the center, and you're preparing for size, whether you're milling or hewing the timber, and so you get from whatever waney edge you have there to the center. Here, you've got a much smaller timber. You actually have the same number of rings because you get from the waney edge to the center. Here again, you've got something that's quartered, and so you might think like, oh, this big timber has a better chance of getting better rings than this little one. If it's cut like this little one has the same number of rings that this big one does. So we're always looking at orientation. And things like this, where you have something, say, flat sawn, that's tough. You end up missing a lot of rings, and it's not going toward the heart. But even out of something like a plank, we are often able to get sample material. There's a lot of plank partition walls in 18th century houses in Mid-Atlantic, New England, and beyond. And so sometimes I can just take a little sliver out of a timber, out of a board in a plank partition wall and get a reasonable sample.
Why would they cut in that radial pattern? What is the function of the wood in a wedge shape?
So sometimes we'll see riven stuff. So I talk a lot about dating houses. We also, it's possible that we can date some furniture. We'll show you some examples where we've done that. So if you're splitting, if you're riving wood, you may have something that is split out that way. Usually when I'm riving, I tend to go just in half. Otherwise, the split line will travel. So if you're riving a piece of wood, it'll go from the exterior into the center. So you might have a skinny piece of wood, like a clapboard, but it might actually have a ton of information in it. So it is possible to get good information out of a NOAA collaborator. Yeah?
I was going to ask earlier, how do you test the wood in a frame, picture frame that's that old?
I'll show
Like the
you.
one Elizabeth I.
I'll show you. So for regular stuff, big timbers like this, I'm using a kit like this. This is what those borers look like. And we've got what we call a bayonet fitting. So this part goes into the drill, and then this is hollow from end to end. So once we get a core popped off in it, you can take this bit end off, and then you can chase it out with a stick like this. And that's typically what we're using. The preparation of the sample, so how I'm able to look at them under the microscope, it's basically like a belt sander mounted, and we'll run through coarse grit all the way up to 1000 grit, put them under a high polish, and then once we've done that, the first thing that we do, I don't know if you can see, there's little marks. You can see one there, one there, one there, one there, and that's every 10, and there's actually dots at 5. So that's one of the first things that I do is put it under the microscope and count it off. We're always trying to visually inspect as we go so that we can rule samples out and say, it doesn't look like there's going to be enough rings. We really do have a threshold. If it's below 55 rings, it's unlikely that we're going to look at it unless we have a situation where we can't find something with adequate rings and complete sapwood. And we might try to match something, pieces from the same house where you've got, here's a sample that's a short sequence with complete sapwood, and another sample that has a long sequence but no sapwood. If we can get really strong matches, that may help for interpretation, but we really try not to use anything under 55 rings and count on those matches.
And the ones on the right were about a 1/4 inch thick, you said?
Thereabouts, yeah. And so this is what I use for the measuring. And so there's this tool here. It's basically a sliding table. This is a screw that runs through it. And then there's this tray. And I've got a trinocular head microscope. There's a camera on top so I can take pictures of things, or I can share real time with the lab in Oxford. And so basically what I do is I align the crosshairs through the microscope on a ring, and there's 2 buttons here, and use the one that's closer, it sends, and the one that's away will clear the signal. So if I make an adjustment and I don't want to use that measurement, I'll hit clear. But part of this piece of equipment is called a linear encoder, and it's just a fancy way of saying it's measuring the distance traveled. So I would turn a little handle, I think that's in the next slide. There's a little handle over here that I turn, this tray table moves along, and then I can align the crosshairs with the next year's growth ring, and I hit the send button where my hand is over there. So much of the time, I am just sitting like this, burning my eyes at the microscope. And that's roughly what I'm seeing. I don't know if you can see, there is a very fine crosshair there. And so I will align it at the beginning of a ring. I'll start, at the earliest one, the earliest one where I've got a full ring to measure and work for the end. Here you can see those rays, and you notice here this irregularity. It doesn't go smoothly across, but there is some irregularity there. And so that's what I expect to see when I'm out at that bark edge. Not a straight or smooth line, but I want to see that irregularity where the medullary rays are. I want to see that carry through. And that lets me know that I've got complete sapwood. And there's a close-up. That's actually through that trinocular head. And you can see there's a dot over here and a dot over there and a line in the center. So that's my 10. That's a 10th ring from somewhere. Okay, so somebody asked about how do you take samples of smaller, more delicate stuff. So we do have another method, micro borer. That tool generally has to be mounted in place. It's a little bit harder to use, and it's going to give you a sample that's a bit smaller. And so here it is. It's set up for taking samples out of a door, and you see there's mounting screws here. So we have to mount it to something. And here is, that gives you a sense of, it's a much smaller sample. Oh, I didn't say, I've got props. How fun is that? Good, like show and tell. And we'll start with you because you're right there. And on these two pieces that I'm sending around, so this shows you what it looks like when they're all polished up. But you'll notice, especially on this was together. We'll start with you. And you'll see there's a big fat ring over here, and it disappears by the time you're over there. So where you take a sample really does matter. Most of this is stuff that I just kind of found on the side of the road. This will show you what I do. I pull over the car, I see a piece of wood, I'm like, oh, I have to analyze that. And so that is what's going around there. That's generally what these samples look like. I don't know if that's enough to keep everyone happy. Here, Russ, you need something to play with.
Thank you. So the more highly polished, the more it's visible.
Yes, so I polish everything to 1,000, and I think everything I'm passing around there is oak. And so you can see that those narrower samples, they're quite a bit bigger than this. This is probably closer to a quarter of an inch. In this particular example, this is the door to the Pix Chamber in Westminster Abbey, which we have a felling range there between 1032 and 1064. One of the things that we're able to do in England that we're not able to do here is if you have a boundary visible between the heartwood and the sapwood, and sapwood is active vascular tissue, and the heartwood is essentially inactive. If you could find that boundary for various species, there is an accepted range of how many rings you would expect to find of sapwood. And so you can make an estimate. In the United States, we just don't have it. The growing conditions are so vast and we have so many species of oak that we have yet to establish a reliable means of making an estimate based on heartwood-sapwood boundaries. So that's why here you see a range, which is unusual. We don't do that in the United States. We do that in England. So increment borer, somebody was asking how do you do it without damaging the trees. That's how we do it. And I think that there are two schools of thought as to whether or not you should plug or not plug. I think we didn't plug. It's the same thing with people tapping maple trees. It's always the same question. Are you risking trapping infection by plugging it up? Should you keep it open? I think the jury's still out.
But you only take one out of a tree. When you said you need hundreds of samples,
So I want hundreds of trees. I want you to run around the forest and get bunches and bunches of samples. This fella here is doing it manually, in situ recording, which is pretty tedious and it's hard to get the same level of accuracy. And depending on the tightness of the growth rings, this can be really, really challenging. But depending on the object, and I'm guessing that I think this is. Oh, okay, Hadstock door, 11th century. This is in England, and I'm sure that the instructions were, do not poke holes in our door. So that's what they did. I've talked briefly about this. There's sort of a new frontier of dendrochronology is isotopic dendrochronology. We're doing a similar thing, but rather than looking at wet and dry years and matching them together, we are looking at the relationship of stable oxygen isotopes within each year worth of growth. And the reason that we're doing this is a couple of things. One, here to the top one, this is probably the more common, is that you get what they call complacent growth, where there's not enough variation. So the difference between wet and dry isn't so pronounced that you can make a strong case, not empirically, that you've got a match to other spikes and valleys in wet-dry. An example would be something that's growing in persistently wet conditions. So even in a drought year, that tree is always kind of in water. And so the changes in its growth are not so obvious. Then you've got disturbed growth, and I see this. I might see this more. You see you've got some funny rings going on here. They're sort of changing direction. I know in one of those pieces that I had passed around, you saw a big fat ring in it. And it could be the tree reacting to a wound, an injury, whatever. That's enough to throw off your measuring. You've got one bad ring in the middle of the sequence. Unless you have 80 rings or so on either side of it to get a match, you can't simply count your way to it. So these are situations where conventional dendrochronology is on occasion just not able to date, and not everything does date. So here's a lot of science here. The nutshell is you you break each ring individually, you cut off the early wood from those rings, and then you mash up the late wood, put it in a mass spectrometer, and it'll give you the ratios of these oxygen isotopes that we look for, and then you use a pattern of those ratios.
He's wearing gloves. Yeah.
Yes. I don't know what the solution that they're using is. So far, this is only being done, well, this was as of 2019. The network has certainly expanded to Ireland, and there are many more sites that have been done in England. But most of this work is happening at Swansea University in Wales, and it's a collaboration between our lab in Oxford and Swansea. And we are just now looking to see if we can get a pilot program going in the United States for this, which would be good here because we have things that haven't dated, that could possibly be dated through isotopic dendrochronology. So somebody asked about the thickness of the samples, how I prepare them, usually about 1/4 of an inch thick. You can mount them, slice them in half down the center, retain half of the sample, and then mash up the rest for this isotopic dendrochronology so that we're retaining material for both types of examination.
When you
So
say, I'm sorry, go ahead.
No, you go.
When you say we in the United States, who's we?
Oh, in the United States, it's Oxford Dendrochronology Laboratory in Maple Durham, UK.
No, but then you said that you were referring to a counterpart here in the United States. Who's that?
Oh, we don't have a counterpart in the United States. So
That's you.
I'm the United States.
You are we.
So no, we have affiliates and associates at Columbia and Cornell. I don't know if they're going to partner on this or not. I'm not sure. We're looking for independent grant funding to get one of these.
That's what I was
pilot
driving at,
studies
though,
going.
is the funding.
The funding is not American
Okay,
right now.
that's useful,
We're
because otherwise.
I think it's particularly useful for us that the funding is staying in England where this is being developed, at least for the moment. If we get something established here, Americans want to pass the hat, we're all for it.
So
you know,
I have a question about the isotopes. What's the generative mechanism for the difference between the two isotopes, and how strongly is it correlated to the wet-dry signal that you have?
it's not related to the wet-dry signal as far as I know. And I do know that they are not actually using Bailey-Pilcher tea, which is what we use for the conventional dendrochronology. They're using straight students. And actually on this one you can see it gives you Bailey-Pilcher at 7.3 and students at 6, and I think they have been relying more on students' tea.
So you have to build this whole sequence from scratch in the isotopic domain.
Yes.
You can't bootstrap off the tree ring stuff. They're not correlated.
Yes, they are.
They are.
But
But
both things are true.
Okay.
So the isotopic chronologies have been developed independently.
Okay.
And then to figure out, are we getting this right? Are we doing this right? It's been correlated that way and that independently. So Dan has taken conclusively dated samples, sent them off to Swansea, and said, what can you get for a result? So they over and over are getting corroborating results. So they are corroborating each other, but it is definitely an independent set of chronologies where it's not super portable.
Right.
And so, here's an example. Again, this dotted line here is that 3.5 level of statistical significance. And this was a project where they did, through conventional dendrochronology, they had a hint in the late 1600s of a date, and they were not confident in it. As a matter of fact, they were confident that it was spurious, and they went through and did it with isotopic dendrochronology and came up with this date of 1368 for this particular structure. If you are jazzed about isotopic dendrochronology, which you all should be, there's a wonderful documentary that was put out by English Heritage on this property, which is particularly significant in its region in Wales. It's my understanding that there's not a lot of good architectural, archaeological record in that region at this particular time, and this is something that Dan had tried to date, the fellow I work with, through conventional dendrochronology, failed to do so, and then later was able to date it to...
So some parts of Wales, for example, get 150 inches of rain a year, which might give you just a constant wet-dry signal, being
so
always wet.
That's exactly that's the complacent thing. That's where the growth patterns...
So that could very well be the case why the isotopic stuff was needed for this particular location.
Yes.
Right.
Yeah.
Okay.
And so if the material is complacent, then you probably don't have any matches between any of the samples with each other because the signals won't be strong enough.
Mm-hmm.
Sometimes you do have what we call floating chronologies, where you get matches where you've got multiple samples, they match well with each other, but we don't have a date. And if you could date one of them, then you've actually dated all of them. So sometimes you get that lucky, a lot of times you don't.
And can you not do that with carbon-14 as well on individual rings?
It doesn't get that level of accuracy. So this will still give you the year that the timber was felled. Carbon-14, I'm getting the sign. How much time do I have?
5 more minutes.
5 minutes. We'll get back to that. All right, we're gonna do speed through Salisbury.
10 minutes.
What's that?
10 minutes.
10 minutes?
Oh yeah.
Now you can relax.
Yeah. Ready to exhale. Okay. I'll still talk fast. I got a lot of slides. So Salisbury, over 600 samples taken when I put this slide in 5 years ago. We're still going. And we've got a lot of samples from this, but what's fun about something like this, keep your eye on this and the colors. It shows you the evolution of a structure. Now you're in spring 1234, summer 1242, 44, 51, 1252. And so you can see, the sequence as it develops of
How
the
can that
construction.
little protrusion be earlier than the thing that it's attached to?
It was just a tower.
Oh,
Yeah. It's a bell tower.
But then you can also see repair phases, which, here it's not been as big a deal, but over there people wanted to know specifically who did what phases. Particularly Christopher Wren has a bit of a fan club, and people want to know, well, what did Wren do and what did Price do? So here you can see the repairs that Price did. I'll be there again in 2 weeks, right back at it. And this is part of the reason that timber framers have to go there, because you need to stand at the bottom of this thing and look up at this just mess of timber. You wonder how it got there and how old it is. And this one's still been a debate. We have not been able to find suitable material for dating in the tower, and there are some heated debates about the age of this thing. So some parts of it have been conclusively dated, but once you get up into the spire, there's a lack of clarity. Okay, now we're back in New Jersey suddenly. So this is in Lambertville. This is a structure that we were asked to date, and it did not have great material. You can see over here, though, we did get dates at 1755, 56. But part of the strategy that I used here was, we saw on the property there was a little corn shed, beautiful structure, dated 1762. It's a nice early corn shed. And I wanted to go out to this because I thought, well, this has more rings. I might have an easier time getting this structure to date to the regional chronologies and then date the housemaster to this. And then I saw the barn and I said, ooh, it's even better. So we have some really big sets of data. I mean, you can see the total set of data that we pulled out of the barn there is from 1477, the earliest ring counted, to 1868, which is part of a repair timber. But we really wanted to try to develop the range for the region a little bit. This is one of the earlier ones that I had done in Lambertville. And so you can see what I've got stacked here, the results for the three structures, the house on top, the corn crib in the middle, and the barn down the bottom. So you see the house is not great. I've got overlaps of 82 rings. That's nice. 3.76, 76 to 6.1. Not entirely remarkable, not without merit, but of course it's not comparing it to this and this, which ultimately did strengthen it. Here we've got overlaps up at 120, getting up to 7.1. And then down here at the barn, we've got overlap of 330, 392 rings. We've got significant overlaps with various chronologies. And then you can see that the t-values are, you know, from 6 to 10.75. And when we put these tables together for a given project, we're not showing you all the things that we ran it against. We'll run it against, you know, 600 different chronologies in a region, and should have hundreds of hits. We'll pick in the highlights here for the report, but all of that replication helps to corroborate. Here's a fun one. I think this is the first one that I did. It was a Comfort Star house, which was believed to have been 1646. But anybody know who Abbott Lowell Cummings is? He was an architectural historian involved with the Society for the Preservation of New England Antiquities and a professor at Yale. And he came along and said, I'll bet it's 50 years later. He was right. The house was dated to 1695. Abbott was a smart guy.
Where was that house?
It's in Guilford, Connecticut.
Oh.
This is the same house, and you can see this is what we want, is this sort of alignment where you've got 1693 and 94. Reason for that is we can't tell you the difference between January and December. The tree is not growing, but I don't know which side of the calendar year it is, so we often do that at 1693, 94, so it tells you what winter, what season that was. I threw this in. This is Parson Barnard House in North Andover, Massachusetts, but to show the importance of, we document the size of each of the timbers at the location where we're taking the sample and the orientation of the sample. And you can see here I've shown where I've missed the heart. You know, these are direct hits, but we want all of that information recorded, including where did the sample come from, what timber? Because if these come out with different dates, that might be significant in the interpretation of the house. Okay, and this is that same house. You can see not everything dated, but then you also see here we've got some means where you've combined samples to make means, but everything is aligning pretty well here. You've got one at 1709, 1710, most of the rest coming out 1711. So this also shows the importance of why we want at least 10 samples per phase. They may not all date, they may not all be from the same construction phase, and you may have a bit of a range. So if you only had that sample, maybe you'd think it was built a year earlier. This is still Parson Barnard. Okay, this one I'll blast right through. This is down in Orange County, Virginia, and Bloomsbury, but it's a multi-phase house. And so I want to show that when you get to a house that has multiple phases, you want to treat each phase individually. They may not match with each other. You might only get one of them to date. So if at all possible, you're trying for 3 phases. Ideally, you would get 30 cores out of this. I don't think we did. But we got a significant amount. We were able to identify a couple of distinct phases. You've got 1809, 1756, and then the last phase at 1826, I think was the end of the material there. And then this just shows where are we looking. So this is just sort of for the dendroprovenancing. This was in Virginia, and this happens to be where all of those individual chronologies were coming from, but they're all matching well locally. We did have a structure once in Virginia that matched only with sequences in Maine, which is where that timber for that house happened to come from. Sometimes, wood floats. Sometimes it floats a long distance. All right, and then, boy, this is my house. This is the neighbor's house. But I noticed that there were similarities between these houses. My house was said to have been built in 1776. This one is said to have been built in 1741. But I noticed some similarities in the house, particularly, some of the nosings and the profiles were identical. So this is where our house is, and this is where the Stokes house is. And I thought, well, it's quite a number of years apart, but there's some identical details. You would swear that door and that door, this is the Stokes house, this is our house, this is the same door. And it's not a typical pattern for 18th century. It's something you see in the 19th century with shallower panels, but and it's very small towns. So I thought, boy, what are the chances that it was built by somebody different? So I went ahead and dated that 1741 Stokes house. What's the date there? So 1744, 45. That's not the date that they said the house was. But there's one lintel over a window in the basement that happens to fit that narrative. So it may be that the house was, part of a house or was built on that foundation at that time, and then it was reconstructed later. It did match our house very well at 9.75 with 161 ring overlap. Okay, there's our house. And we had a lot of information about this house, supposedly built in 1776, and we had July 6, 1768. That's when the patent was offered on that property. So we had no reason to think that the house would have been any earlier than that. However, trouble arises. 1734-35. Well, that doesn't really fit so well with the date stone. We have really strong matches here. We're in over 10.14, and discovering that this is the hearth in the basement in 1734-35, which led us to understand that there was a land lottery held by William Penn's no good, rotten, awful children when they ran out of money. And they sold off lottery tickets for land that was part of the walking purchase, which didn't happen until 2 years later. So they stole that land at least twice. The point is, the Dendrochronology tells you where in the historic record you need to be looking. If we've got felling dates at a certain year, and you've got a pile of documentation, documentary evidence, that felling date can help maybe narrow your search in that documentary evidence. Okay, this is Durand-Hedden. This is the last one. So these are the samples that we pulled out of this house. Not great, and we knew that going in. We gave warning. So I think we're over here somewhere, but these are two sort of distinct looking sections of framing, and this shows you where we had taken the individual samples. We went for more than 10, which is what we usually describe, and these were ones that we got out of the attic, but they weren't great. And as you can see, there's a lot of blank spots here because they didn't all date, which is why we went and took as many extra as we did. But we were able to get dates. You see, after 1783, there's no C. It means it was incomplete sapwood. So that after 1783 just means it's the last ring counted, but we know it's not the last ring of growth. But the rest of these align really nicely at 1793-94. And this is the rest of those rings. And then you can see what some of the best matches were. Actually, the one that I showed earlier was that Homestead Farm. And you've got that chronology, 1477 to 1868, and 198 ring overlap. So these are really strong matches. So I'm not just looking at the value in the t-value, but we're also looking, how many ring overlap are you getting
Where's the
at?
Hutcherson Memorial Forest?
No idea. Not a clue.
Me either.
And I know, so this is World Data Bank, Ed Cook.
Yeah.
Same here, and same here. So Cornell and Columbia, and Lamont Doherty Laboratory, they did a lot of work on building and developing the regional chronologies. And so that information, much of it was shared. If you go to the NOAA website, there is the International Tree Ring Database. That information is there. Anybody can have it. Additionally, There's cooperation between our laboratories where we have other chronologies that are unpublished that they have shared with us. But we haven't necessarily been to all of those sites. But again, in this house, you see that alignment that we're looking for.
What was the date of this house believed to be before you did this?
1787-ish?
90, I think.
Well, when we did the master plan, they found a building on this site from 1780, in the 1780 map, that was owned by Hedden, who is the Durand-Hedden, probably his father. But what I think Michael and Dan thought, and with what Barton, our historic architect, thought, was that maybe there was a building from 1780 and that it was taken down when this was built. That's all we can figure out, because what you found was 1792 to 94.
Yeah, and we, you know, one of the things, so when we do the dendrochronology work, at the end of it, you get a lovely report. It includes information about the samples and the results that we have. Sometimes things don't date, and we would convey that and just say it was inconclusive. And we're somewhat limited in our willingness to make interpretations beyond what's really offered empirically. So we can say, if your samples are coming in at 1820, that no, your house wasn't built in 1799. And that's about as far as we push it with the interpretation. It's sort of, the rest of it's beyond the scope. What's particularly important that is included is methodology. And methodologies are not all the same. Softwares are not all of the same for this. I am using 2 programs. I am definitely the only person in this country using them. And there's only 1 or 2 other people in England using these programs. But it's explained in detail what the processes are so that it's repeatable. If you can't repeat it, it's not science. And so it's important that that's spelled out. Yeah?
You said you're going to England soon,
I'll be there on the 21st. Yeah.
and that's at your own expense?
Are you tipping?
Pass the hat. So, yes, there is a group over there called the Vernacular Architecture Group, which was the inspiration for our very own Vernacular Architecture Forum. And I had been told that this tour was coming. It was a tour not to be missed. It's a very small tour of a lot of private homes in Wiltshire and area around Salisbury Cathedral. And it's a big 5-day tour. But Dan, the fellow that I'm working with, has been at Westminster Hall. They've been, so there's this beautiful hammer beam truss angel roof in the hall that Dan has been poking around. He's taken samples of it over the years, but they've got scaffolding set up right now because they were doing some cleaning but looking at some utilities. So I'm going to crawl around in that. I don't know, it's got 2 weeks planned out, and I think I only have a minute or 2 to sleep and have a pint. But, yeah.